Okay, so key thing with your setup is the thing that goes down here is the thing you are trying to figure out. So this is where the unknown goes. The burette is where you put the known substance. Now you can do acid to base, base to acid, just depends on what you're trying to figure out. Okay? And then, like Jordan said, you very carefully drop it to figure out the equivalence point. That's really the main objective. Now we're going to learn there's other things along the way we can learn, but the main thing is to get to that equivalence point. Because the equivalence point is the point at which the moles are equal to each other. And so since I know this one, once it gets to the point that it's equal, I can find that one. And we'll talk about the math behind that when we get to that point. Okay? And once again, it can help us determine an unknown concentration. So I have this acid. I don't know what its concentration is. By doing a titration, I can figure it out. At SUU, we use them actually fairly often. So in link with like their science department, they have what's called the water lab, where companies pay and send in samples of water, and then we would analyze them for different things depending on what they're worried about or looking for, right? Of this extreme to like, is there too much arsenic in this water, right? Or like if you're going to plant crops somewhere, like how's the iron content or different things like that. And titrations is one of the ways to measure that. Because you have this water, you have no idea what's inside of it. Titrations can help you figure out how much, what's the concentration of the substance in it, okay? I'm really disappointed because I was super excited about this, but we'll see if it worked. Didn't work last period. No. I had a really cool drop the bass sound, like from a song. Just, yeah. Okay, so what we're going to do here is we're going to visualize drop by drop the molecular level of what's changing. Okay, so we're going to start. So each of these circles corresponds to a different box. Okay, now the first type we're looking at here is a strong acid with a strong base. So for this, we're going to say we're going to react HCl. So write this equation here right below. You have a lot of space there if you want. And NaOH. Okay, we're going to say our acid is the substance we don't know. So that's going to be in the beaker below. And then the base is up here. Now, you could do it the other way. The graph would look different, though. Any guess how a graph would look if it was flipped? Pretty much flipped, right? It would start high, because bases have high pHs, and then drop low. Okay, but recognize what we're learning here, it's just would flip if it was the other way around. So right now, these boxes are going to represent what's in the beaker. Okay, so this is our beaker view. So with your table buddy, for a smiley face, I want you to draw me a picture of the molecular view of my beaker before I drop any base in. Ready, set, go. Talk to your buddy. In that square, yep. You might want a pencil today because you might have to change things. You don't have to draw a beaker in the box, by the way. Just take the box as it is. Talk to your buddy. Make sure you both agree. So before I drop base in, set your pencil down when you're done.
If you only have an acid with a pH 0.
No. What does pH measure, Sam? Good. So it's just based on how much hydrogen you have, right? So the more hydrogen you have, the lower the pH will go. Okay, so I think we all understand that the only thing that's in here is what right now? Just strong acid, right? So before you drop base in, now we're not going to draw water. Water's there too. And anything that's maybe in a very, 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 very small amount. Okay, we're going to just draw what's primarily there or what's primarily affecting the pH. Now, HCl is what? A strong acids. What do strong acids do in aqueous solution? Fully dissociate. So you should have your HCl drawn like this. So if you didn't separate it, fix it so it's separated. And if you had it separated to begin with, you can have a smiley face.
Yeah, is it dissociated or disassociated?
Dissociated? That was like question mark? Disassociated or what? I don't even remember what you asked now.
Is it dissociated or dissociated?
I think it's the same thing. Yeah. Yeah. Separates. Good question though.
Do we always assume that there's water? Like it's aqueous?
Yeah, because all acids and bases are aqueous.
Okay.
Always, every time. So, good question though. Okay, everyone understand here? So, if I needed to find the pH at the beginning, mathematically, it would just be that equation Sam brought up, right? That the pH is the negative log of H+. Because since it's strong, all of it turns into H+. Which once again is why the pH starts so low. Is because it's a strong acid and it's fully dissociated. Okay? Okay, now let's look at this box. So with your table buddy, so we're starting to drop the base. Draw me a picture of what's gonna look like there. Ready, go.
Yeah. It's gonna have and there will be some yeah, some water. Okay. Except for solid still, you are right.
So I think that.
Once again, don't be afraid to be wrong because there's a lot of power when you have to erase.
Same as right? Yeah, there should be a same because the only ones that actually go away are like
All the basic reactions from the acid side there.
Okay, everyone ready?
Maybe.
Wave your arm if you want a few more seconds. Okay, a few more seconds.
I always remember it's still like
Okay. Okay, someone tell me one thing. So it's one thing that should be in the beaker still. Eli?
A little bit less of H pluses.
Good. So why do we have less? We still have some, but why do we have less?
Because we're adding a base into the strong acid, which is slowly depleting.
Good. So whatever ratio of H you had here should be less. So I have 4, so I'm going to draw 3 now. Good. Have a smiley face for that, Eli. Okay, what else do I need in this picture?
the CL isn't being touched, is it?
Good, yeah. Nope, it's not. So you should have the same amount of Cl. What? Okay. Hannah?
You have an Na plus
Why?
because when you drop in the NaOH, the OH bonds with the H plus to make water, and you don't write water, but you still have the sodium ion.
Good. So every H that has gone away you should have the same ratio of Na that's now floating to show that common ratio. So I'm going to have 1 Na plus. Have a smiley face for that, Hannah. Okay.
And then the OH and the H, they just react and like turn into water.
Good job, Macy. Have a smiley face for that statement. You stole it right out of my mouth. So why do we not have any OH floating around? Yeah. Every drop of this that goes in turns into water, right? So here's just, if this helps, there's just another way of looking at it. So this was like, just drawing like a bar graph to show amounts, right? So I had this much HCl to begin with. If I add this much NaOH, it's going to react with the same amount, but then it actually goes away
Because it needs to reach equilibrium.
because it's turning into water, right?
It's not neutral.
Yep, it's not neutral. Now the Na, right, on the other side is with NaCl, and as I heard you guys say, NaCl doesn't stay together, so that's why they're just both floating around. So, okay, questions before the equivalence point. So at this point, the base is starting to neutralize the acid. But it gets used up with every drop you add. In a sense, our base is still our limiting reactant. That's why our pH is still low, but it's starting to climb, right? Okay. Oh, if you had this picture, you and your buddy get a smiley face, by the way. Okay? Okay. Draw me a picture now at the equivalence point. Ready, set, go.
Alright, so you have
More NA. Well, because there'd be no H plus floating around. Yeah, so just
What do I have there at the equivalence point?
we should have the same amount of NA. So.
Okay, I'll take the, are we ready? Okay, someone raise your hand, tell me. What should I have here? Andrew?
Salt that's separated into an A plus and Cl minus
Good.
and water.
And I heard a lot of you say this, the ratio of Na to Cl should be the same, right? So whatever your ratio is,
Because you got rid of all those hydrogen atoms because of the water.
good. So you shouldn't have any hydrogen floating around. It's all neutralized. This is all that's there at the equivalence point. Because what is the definition of the equivalence point? What's equal? The moles of the acid equal the moles of the base.
So does that necessarily not mean there's the same amount of each thing?
Moles are equal, concentration may not be equal though. Does that make sense? Because concentration is moles per liter, and so you could have different volumes of them, but the moles should be identical. Which means if I have equal of this to this, you don't have a limiting reactant, they're both limiting, so they're both gone, and you only have these two things floating around. Which means for a strong acid, strong base, what's my pH at this point? Exactly 7, yeah. So strong acid, strong bases always fall right at 7. Now, we've talked about an equation in the past when we're looking at equivalency of moles. There's a formula that we've used that's not on your formula sheet. Anyone ringing a bell? No. We'll talk about that one later. I remember a formula we've used that allows you to put moles to solve for moles that are equal to each other. That's okay.
What was that?
Polarity equals mole rate.
M1V1 equals M2.
Oh. She starts to write it.
All right.
No, I thought it was a different one though.
Okay.
That's the one I was
So,
thinking
this is the equation we can use to find what the unknown substance is. And we'll practice that more when we do the lab and actually have data on it. So, okay, questions at the equivalence point? If you have this, by the way, give yourself a smiley face. Okay, and then draw me the last picture. Ready, set, go. Okay, so past the equivalence point, what's happening there?
Then,
Okay, all my HCl, or all my H is more and my CL still floats. Now I should get more.
yeah, so H plus would now be OH.
So what they're saying.
Or H
And
and
then you make it like
the C on the floor.
Yeah.
Wait, no, that's what these are.
Because that's
CLs, like cases are.
with OH.
Oh, yeah,
Yeah, because you keep passing this. You're right, maybe you take this amount of NA already, that you already have, and then how much of it you have. The same amount of NA. Just leaving those.
Are you gonna do in your places? It's gonna be more space.
Okay. Do I take the silence as we're ready?
Sure.
Almost. I see some drawing final little circles. Okay, so after the equivalence point, somebody's gonna tell me what's there. Bonnie? Good. So at this point, we're just pouring more base in, right? Which is why the pH just goes up so high. So we should have more NAs than we did before. So we had 4 there, so I'm gonna say we have 6 of them. Whatever more is, you have more. You also now, the OH has nothing to react with, so you would need just, in this case for my ratio, 2 OHs floating around, right?
Would there be any CL? Would there be CLs?
Why is there still Cl?
Because it's not. It would you say it would react with the NaCl, but they're just
Yep. Now does the number of Cl change?
no. It's just the same. You're not adding any more.
Yeah, still just that. So have a smiley face for
They're
that, Bonnie.
saying I'm exactly.
Questions on this? If you have this, give yourself a smiley face. You know, Macy, this is a good thing to be getting right, so that's good. Okay, any questions so far? Okay, turn the page and let's look at a weak, strong titration. Now, before we dive into the molecular view, let's just look at the graphs really quick. So kind of flip back and forth. What differences do you see between a strong and weak graph and a strong and strong graph? Eli, what do you see?
The one thing is on this one, it kind of just shoots straight up on the strong acid, strong base. But on the weak acid, the strong base, it kind of like goes slower.
Yeah, this one has a much more distinguished vertical line. Vertical, what do you call that in math?
Vertical line. Yep.
That's the word I was looking for, not line. But, okay, good. What else? What other differences?
The equivalence point is not at neutral.
Good. Where's our equivalence point on the second graph? Above 7, right? So good. We're not neutralized with the weak to strong. Any other differences people see?
Shoots up quick and
There's dots instead of.
Look at the second circle very carefully.
like this one's going up, well, this one's going like slowly down.
Yeah. So like in math, right? So this one is just kind of going gradually up, 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 up.
This one's already.
The second one,
It's already like over.
It's already going up, but it's gradually getting.
where's my graph?
You did that same amount of time. It's going up 100.
I lost my mouse. There we are. Okay, so this one has like an inflection point. So So it's actually like concaving down and then it concaves up.
That goes.
When the other one just kind of is going up. Okay? So kind of think about those as we go through this so we can explain at the molecular level why there are those differences. Okay? Now, you and your buddy are going to walk through all 4 steps of this, and then we'll talk about it. Okay? So with your buddy, draw out all 4 steps of a weak acid titration at the molecular view. Oh, I'll give you an equation to use though.
Just come up with one.
Well, we are going to actually use just a generic one, but so for weak acids, we're just going to call it HA.
Oh, okay.
So we're going to react HA, that's my weak acid, so that's down here. And we're going to react it with a strong base. And in this case, we're going to actually we're going to remove the spectator sodium. So we're just going to focus on the OH minus. So you don't have to draw sodium in any of the boxes this time. Okay? Okay. Ready, set, draw.
Okay.
So acid's down here, so we're still dropping the base.
Yeah, so just UHA, and then would you break that as well away?
You tell me.
Have less
That's a very good question, Riley. I'm glad you're thinking about it. Now you just gotta figure out what happens.
Are we allowed to ask you?
You can, I'm not gonna answer yet.
Where's that reaction?
But I can tell you that.
So that must mean that only some of the dissociation.
So,
Once again, it's okay to be wrong, and it's better to be wrong and try than to leave it blank and not try.
Okay, so we have weak gas.
and then up here,
It's not gonna get it. That's just, I think adding those is going to, and it's not gonna be that. It's like.
So now we start at the base.
The O minus have red. OH minus would have some.
Yeah, so water.
So add more base, acid's gonna get out of here.
It'd be the same amount of.
Let's just take away
What was the
we have
question?
our NA. Our OH is
Why did our last go?
They're doing the same amount of
Think about the behavior of the I just don't want to
Yeah, the A minus much strong than it is. Because this hardly ever happens. Makes sense. I hope so. Right. And then this one. Is it just all in? Yeah, just for fun. Well, actually, oh, yeah. Maybe this is the at this point, when all of the acid base is to the same, but there's no more, but there's no OH minus. And then it becomes even more basic when you start adding more.
Okay, set your pencil down when you're done or you surrender.
I surrender.
There's opportunities for smileys if you get part of the picture right. So you If you're not sure, be like, well, I know this at least has to be there, then draw that.
It's a big OH minus.
Okay, here's what we're going to do before we walk through it together. I'm now going to pair your partnership up with another partnership. Compare your sequence with theirs, and if you have differences, discuss and see if you can get on the same page. If you can't and you agree to disagree, that's fine too. And then we'll go through it all together. Okay? So you turn around and talk to them. You two turn around and talk to them. You two turn around and talk to them. You two jump around and talk to Martin and Adam. You two talk around and talk to them. And you guys talk to each other. Okay? Alright, ready, set, share. Discuss. Change things if you feel like it needs to be changed.
But then there's one left. Yeah, some may change, but I don't know.
Okay, finish up your discussion in the next minute.
I think there would be, because these are bases right here, but they're weak bases. But then I think but that's like so it would be like that's what I saw.
Okay, that was real rhythmic. Okay, turn back to your seat for me, everybody. I just want to make sure we don't leave on a cliffhanger before the bell rings. Time flies by when you're dropping the bass and having fun, right? Okay. Let's walk through our different phases. I'll let you know what you get smiley faces for as we go. If there's questions, let's make sure we understand the why. Okay? All right, so initial pH. The main thing floating around in here is what? The weak acid, which weak acids exist primarily as HA. So you should have mostly HA in this flask.
Still some disassociated that you still don't.
So, yes. So it is important to recognize this is weak, right? So weaks do break apart. If this didn't break apart, what would my pH be at?
0.
7.
Or 7.
I knew you meant that, Josh, right? Because in order to have a low pH, you have to have H plus floating around. Now, the ratio though, how much H plus do I have in comparison to HA? Tiny, right? Remember our Ka values are like 10 to the negative 5 or more. So technically, based on my picture, ratio-wise, I wouldn't draw any H pluses, but they are there, so if you did draw them, it's fine. But like on AP questions, typically they won't even show them in here because in comparison to the ratio, it's really, really small. But it is, you're totally right. So it's just weak acid and a small amount breaks apart. Good, so if you have that, or if you did it like Macy did, you can have a smiley face. Questions there? Okay, we're starting to drop the base. What's happening at the molecular level? So the HA reacts with the OH and turns into water and A minus. So for every HA you take away, you need to add an A minus. Okay, so I'm going to take away 2. So if you took away some HAs, you can have a smiley face. If you added A minuses, you can have a second smiley face. What should definitely not be drawn in this picture though? H plus or OH minus, right? Now technically there is still H plus because it's breaking apart, but anything that in a lot would get neutralized, right? Now this segment is key. What do we call a solution that has HA and A minus floating around at the same time in similar concentrations?
A buffer.
A buffer. We make a buffer in the middle of our titration. That's why we have the inflection point. Because rather than the pH just gradually going up, it stabilizes it till it breaks. So this whole section, label that box, this is known as the buffer region. Now, there's a very special spot within the buffer region. The point at which these two are perfectly equal. So if you think of the Henderson-Hasselbalch equation, where pH equals pKa plus the log of this over that, if these two are equal, what's the log of 1? 0. So at the halfway point, the pH of your solution actually equals the pKa. So this is a way where you can find the Ka of a substance if you don't know it experimentally. Okay, so take a pencil. So we're going to say, so our equivalence point, I'm going to round, it's pretty close, but it falls right at about 11 milliliters. So draw a line at 11 milliliters, that's about where our equivalence point is. You can draw it to where it really falls, but it's close to 11. Everyone see that, right? Now we're going to go halfway to the equivalence point. So what's half of 11?
5.5.
Okay, so go to 5.5 and draw a star on your titration line. That's the very middle of the buffer region. I'm going to have a star drawn on their line. Then connect your star over to your y-axis. What approximate pH are we at? About 5, right?
Yeah.
So that tells me that the pKa of this acid is about 5. So the equivalence point is like the most important part of a titration, but with weak to strong, that's like the second most important point. Because if you didn't actually know the identity of your acid, you could figure it out. Because there's charts of Ka values and they're all unique. So you could look up, okay, well, what substance has this Ka value and figure out what acid you're testing. If it was like, I just found some white liquid or some clear, not white, white sounds weird. Some clear liquid at a crime scene and I don't know what it is, right? You could actually identify the specific type of acid, not just its concentration. So, okay, questions on that? So once again, what we said here is that the pH will equal the pKa at the halfway point. The reason why, once again, is because at the halfway point, the HA equals the A minus. At the very middle of it, right? The buffer region is going to go up and down because as the buffer gets used up. But at the very middle, those are equal. Okay, questions? Okay, equivalence point. What do I got here? Eli, what do I got?
Wouldn't you have the same amount of A minus as you did HA?
So, the original amount of HA, so what is equal at the equivalence point?
The moles of acid and base.
Good, moles of acid to moles of base. So at this point, all the HA and the OH are equal, right? And if these two things are equal, are they there anymore? No, they're gone. They react and turn into the same amount of A. So as many HAs as you originally had should now all be A minuses. So you can have a smiley face if you have that ratio. Now I heard some good discussions. Anything else people believe should be there?
Water.
There is water. Good point, Andrew, because we are making that too. Have a smiley face. You're not wrong. Do I have anything else in this? Bonnie,
Wouldn't you also have the ion for the, with the OH
from what?
from the strong base? Would there be an ion because we're not drawing it? Would you
So-
also have that?
You're wrong,
Okay.
but you're getting to the right point. So we don't have any of this because if these are equal, they just bond with each other, right? But I think I see where you're going because where's the pH at this point? So then how's that happen? How is the pH above 7 if we don't have OH floating around? Connor?
Don't we need some, so, don't we consider it above 7 because the A minus is the conjugate base, so it'll rip some H off of H2O?
So what Connor's saying here is totally correct. So the thing we have created is a weak base. So what we almost get is we get new OH made because A minus is a weak base. Now once again, ratio-wise, how much O minus is there in comparison to A minus? Teeny tiny. It's the same reason why drawing H plus here is a little off for ratio. But if you want it is there because that's why the pH is above 7. So since A minus that's created is a weak base, it can react with the water that's around and produce a small extent of OH minus. Questions on that? The biggest misconception is people saying, oh, it's above 7 because of the strong base. You don't actually have any more strong base. You have a weak base making new OH. So it's not original OH, it's new OH that's being made. So, questions with that? Now the moles thing is still true here. So M1V1 equals M2V2 still holds true because that doesn't change, right? Because the moles are still equal. So, good? Okay, last box. What should I have here?
Same amount of A minus and then.
Good, because this is just still there, right? So if you have the same amount of A minus, you got a smiley face. Macy, you're gonna say something else. What else should I have?
And then just OH.
And now we're just dumping OH in, right? Which is
And
why.
it doesn't matter how much OH is coming in.
Yeah, because it would kind of depend on like what point of the titration you're on at this time, right? So, because once again, after the equivalence point, it's just excess base. Questions on that? 53 is when the bell rings, right? That was good timing. Okay, so homework tonight is so this isn't due till the 17th. Okay, I put it just to remind you. I've also left this quiz and the reading open till the 17th as well. Okay, I want to highly encourage you, for those of you that don't always, and I know most of the time we do, but we have times where on AP quizzes we just go and click because we need to get it in before it's due. I mean, it's probably not you, it's always B6 who does that, right?
We would never.
Right. But this quiz is like, I didn't do a homework assignment on titrations. It's just this quiz. So take it seriously. There's 17 questions. But because there's not a worksheet as well. Because a lot of times we'll have a worksheet and a quiz on the top one. And you have till the 17th to get it done.
And then smiley faces.
Okay, so leave your smiley face trackers, pass it in the middle before you go. If there's a chance you want to use it. If you know you're not going to use them, don't turn them in. But if there's a chance.
Wait, Miss Alves, are grades like final, basically?
So it,
Like it can't go down anymore?
the only thing that might not, some people it's in, some it's not, is the calorimetry. If that's in, it can't go down.
Yeah, okay. Since I was gone, could I do a check?
I guess so. Yeah, I guess you can score them. Like the paper? Did you check the basket?
So the 90 there, but I could be like.
Okay, I might be out too. It is also like, because it's a report,
Do we hand them
so
to
you
you?
type it up.
Okay.
Does that make sense? So if you lost it, then we might need to just get the data from someone so you can do the report. Does that make sense?
Did you say you hadn't graded all of the labs yet?
Not all. So if it's still a star, that's going to go in today.
Okay.
But that's the last new thing that will go in besides like corrections and stuff.
My unit 7 says I didn't do the notes. I have a 0 on the notes.
Like the vocab and stuff?
Yeah.
I should be able
And I
to
know
play
for a
on
fact that I
Wednesday.
Maybe
if I
name
play
or
on
something,
the
or it just got missed. Check your folder, that's the easiest thing, because if it got filed, then we can easily put it in. Because that's where it would, if it got turned into me, it would get put in there.
Greetings, Coach.
Hi, Aubrey.
How are you?
Andrew, if you want to swing by after school, we could get you just the data on it.
Wait.
Or do you think you have the data? Okay. Okay, yeah, if you get the data from someone, then if you go on Canvas and go back to that unit, there's a link to the report.
Where are the multiple choice corrections to?
They should be in the back of the what did I miss. It's normally, unless I ran out of copies.
What time are you here in the morning?
7:15.
Okay, I also have this monstrosity of a packet. Just need to put my name on it.
Wait, do you have both terms or only one term?
Just one term.
You can keep it till you get both then.
Okay.
Because they won't put it in the computer till you have both, I think. So hang on to it, and then when you get term 2 done, you can turn it in. Do you see it in there? Okay, perfect.
I hate cramps, Coach. So I have one right now.
How much water are you drinking, honestly?
I don't know.
I don't think you're drinking enough.
I don't think so either.
Do you carry a water bottle around school? Then you're not drinking enough. And that's why you're getting so many cramps. So we need to get you a water bottle.
I was feeling like kind of silently judged, just like chugging my water because it was like so loud.
I didn't even hear you. But you could like hear yourself like.
Yeah.
That's funny.
I'm just like the entire class is just watching me.